Good day and welcome to another episode of CHE 101. I am Luther King Hardin, and in this video we will be tackling dimensional analysis, a topic in momentum transfer or MOMECHE. Here is the outline for the video. Dimensional analysis is often used in engineering to determine the relationships between process variables, be it pressure, temperature, or characteristic length. It is also used to reduce the number of variables needed to create a mathematical model based on experimental data. Before everything else, we need to know that four fundamental quantities exist for dimensional analysis. These are the mass or force, temperature, time, and length. These are called fundamental because any quantity can be created from these four. For example, pressure is equal to force per area or force per length squared, acceleration is length per time squared, and the density is mass per length cubed. Let's say F1 is a function of F2, T1, and T2. It is equal to 3 times F2 times T1 over T2. Notice that T1 and T2 cancel out in terms of units, meaning that both sides are basically congruent. The same applies to this expression. They are both equal to some amount of force. Let's say F1 over F2 is a function of T1 over T2, or let's say 3 times T1 over T2. Both sides cancel out to be unitless. The same goes here. Therefore, the fundamental quantities can be manipulated as long as they are dimensionally consistent. The numbers that were calculated such that the units cancel out are called dimensional numbers. These quantities are extremely important in chemical engineering. You will encounter this especially in MOMECHE, HITCHE, and many other courses. Here is a list of dimensionless numbers, which are calculated as functions of quantities such as density, viscosity, or thermal conductivity. For example, we have NEU, or the Euler number, which is the ratio between pressure and inertial forces. It can be expressed as pressure times Gc over density times velocity squared. If we express the units as is, we have this. Notice that Pascal is equal to newtons per meter squared, and if you cancel out the units, you'll end up with nothing. Another example is the Reynolds number, the ratio between inertial and viscous forces. It will be widely used in MOMECHE, so keep this in mind. It is density times diameter times velocity over viscosity, and these are the corresponding units. And if you expand it further, you'll end up with this, which also ends up being dimensionless. But how can we take advantage of these numbers? Basically, we can create functions relating these dimensionless numbers to simplify natural or process phenomena that are normally expressed with many quantities. There are two ways to make these functions. One is Rayleigh method, which expresses a functional relationship of some variables in the form of an exponential equation, and the other one is the Buckingham-Pi theorem. It states that if there are n variables in a problem, and these variables contain m primary dimensions, for example m or LLT, the equation relating all these variables would have n minus m dimensionless groups. Now let's solve a problem to better illustrate this method. The power P required by an agitator in a tank is a function of the following variables: diameter of the agitator d, the number of rotations of the impeller per unit time n, viscosity of the liquid mu, and density of liquid or raw. From dimensionless analysis using Buckingham's method, obtain a relation between the power and the four variables. The power consumption is found experimentally to be proportional to the square of the speed of rotation. By what factor would the power be expected to increase if the impeller diameter was doubled? So we first let the variables be a function such that they can be equated to zero. We are asked for the relationship of power to the other variables using Buckingham-Pi theorem, and the power of factor of power increases if the impeller diameter is double. Again, here is the statement for the Buckingham-Pi theorem. We have five variables, three dimension, which are m, l, and t, or the mass, length, and time. Note that we don't account for the temperature in any of the five variables. Therefore, we have n minus m is equal to two dimensionless groups, which we call pi terms in this process. Let's break down the variables into the fundamental quantities. The power is energy per time, and energy is force times length, and force, as we all know from the second law of motion, is mass times acceleration. We then have this expression for our power. The diameter is just expressed by the length or the meter, and is just hertz this since it is a number of cycles per unit time. Density is mass over volume, and the viscosity is pressure times time, and if we break pressure down, we get its dimensions. We need to choose m, or in this case, three recurring variables to be raised to exponents. Note that the recurring variables should not be able to form dimensionless groups or expressions by themselves. For example, you can't have the diameter twice and have d over d. That's not allowed. We choose rho or p rather, d and n, which is normally chosen in Buckingham theorem as our recurring variables, which we raise to exponents, and we have two pi terms for rho and mu. If we break them down, they must be equated to be unitless, meaning that the total of the exponents for each quantity must be zero. For this, you must make systems of linear equations. For the mass, the total exponent is 1 plus x sub 1. Equating it to 0 would yield x sub 1 is equal to negative 1. Same goes for the other quantities L and T. Take note of the multipliers which are related to the dimensions. Now that we have the values for the three variables, we can construct the pi term as follows. This is actually a dimensionless number called the power number, which will be used later in MOMECHE. The same procedures apply for 5 sub 2, which has the viscosity. If we break it down into quantities, we get this, which we can express as a system of equations. Pi sub 2 is equal to this expression, which is called the impeller Reynolds number. Then we determine the relationship between the two dimensionless numbers by relating them as a sum of quantities equal to 0. So for this, we have a coefficient and exponent. So this is a sum of the dimensionless numbers with for each being raised to a certain exponent a. If we transpose the one term to the other side, we can isolate the dimensionless number which has our dependent variable p. Notice that it can be isolated by dividing negative k sub 2 and k sub 1 as well as the exponents a sub 2 and k sub 1, which we can just express as k and a. Multiplying the denominator, and we have this expression for p, which is isolated on the left side. We can therefore determine how p changes based on its relationships with the other variables. For example, let p be proportional to n squared. To have n squared, n cubed in one factor must be divided by n raised to 1, or a is just equal to 1. Simplifying, we have p sub 1 is equal to k d cubed n squared times mu. Therefore, if the diameter increases, our new p must follow with a relationship of a square. So, for example, if the diameter is doubled, we can follow this, and then 8 can be taken out from the original expression. Therefore, the power increases 8 times if the impeller diameter is doubled. Here is the complete solution for your convenience. In summary, dimensional analysis helps determine relationships between variables and reduce the number of variables in modeling or correlating data. There are 6 steps in dimensional analysis using the Buckingham Pi theorem. One is to tabulate the variables and their corresponding dimensions. Choose the m recurring variables to be raised to exponents. The recurring variables should not be able to form dimensionless expressions by themselves. Substitute the dimensions, and since the pi term is dimensionless, the sum of the exponents per dimension must be zero, from which it can be solved by a system of equations. Solve for the values of the exponents using the previous method, and finally, formulate the pi terms and manipulate it algebraically. If you have any more questions, feel free to contact the following. Thank you for listening and good luck in your studies.